Hello, everyone, and welcome to today's HP Idle webinar. My name is Will Scoggins, and I'll be your host for today. Before we begin today's session, let me just quickly cover a few housekeeping items. To maximize your bandwidth for this presentation, disconnect from the VPN and shut down instant messengers or any other programs you have running that are communicating over the Internet. If you'd like the slides to appear larger, click the white box that is located in the upper right-hand corner of the presentation window. To ask an online question, simply enter your question in the QA window and then click Ask. Today's session is on the science behind HP Idle. Our speaker today is Dr. Sean Blanchflower. He is the head of research and development. It is now my pleasure to turn it over to Sean. Sean, please go ahead.
Hi everyone, and welcome to the next session in the Idle Under the Hood series. For those of you who are not familiar with Idle, it's an advanced piece of server technology that is designed to handle human information. I'll talk a little more about what we mean by that and what it can do. But the real aim of what I'm wanting to speak about today is to give you a little insight into the science, the mathematics behind Idle. The stuff you don't normally get to see, to give you a little bit of an understanding as to how the technology works underneath. I once went to a talk by Stephen Hawking, and he said that every time he shows an equation in a presentation, he loses half of the audience, and so by the end he feels he has very little people still following. So I'm afraid there are a few equations in the talk today. So if that scares you, don't be too afraid. I'll try to explain them as best I can, but bear with me and I hope we'll learn something. Just a quick run through what we'll be covering today. We'll talk very quickly about human information and then a little on what Idle can do as a piece of software. Then I'm going to jump straight into the theories underneath Idle, in particular those of Thomas Bayes and Claude Shannon, and then end with a few examples of exactly how that works in real life. So it's a quick one on human information then. What is human information? Well, human information is that type of data that is created by humans for consumption by humans. Examples of that are emails and videos, Twitter and Facebook posts, and then we can bring in videos as well. So TV streams, closed-circuit camera footage, or audio, the kind of conversations we have over mobile phones. This is all information that is designed to be accepted by humans. To understand how Idle can help this, a quick history lesson is useful. Back in the 60s, when computers were first able to accept information, the only type of information that could be put into the system was those in very structured form. Databases, very primitive databases were set up so that it could take, for example, a piece of information on the amount of stock you have in your warehouse. So it would have a field saying the name of the stock, maybe a code for it as well, and then it would have a number for the number of items left. And every time you wanted to change that, the stock would go up and down, and the computer could tell you when it was about to run out. That changed very little over the next few decades, until the 90s and the arrival of the web, when suddenly the type of information that computers were dealing with was not in structured form. We were dealing with emails for the first time, and then of course web pages and all that's come along since. And so the time was right for a move away from the structured handling of databases to something which was built from the ground up to be able to deal with unstructured information, human information. And that's where was the birth of Idle Server. And here's an example of what we mean by human information. So if we were encoding the name of a company, in this case HP, we could place that with two letters which can be stored in a computer in a very small form, probably 16 bits or something like that. But to a human, HP means so much more. The understanding that a human has of a pair of characters like HP is so much broader that just to encapsulate it by those two letters misses out a huge amount of information on what we're really trying to get at. The idle takes the information and it's able to build up an understanding based from its context, based from its the occurrences of the information and the training that it gives it, in much the same way a human can. So here's an example on the screen that we took a lot of feedback from a talk given by Meg Whitman, and we analyzed it using idle. And these are a few of the concepts that came up. Now, so those of you familiar with different parts of HP, you can see that there's a lot of stuff that is relevant to it. It's just not captured in those two letters, H and P. Another example then is when we move into pictures. So for one person, this is a picture of a cartoon dog. For another person, this reminds them of the cuddly toy they had when they were a kid. Another person, it's the comic strip they read on the way to work each day. There's so much more than just that image in understanding in a human way what that is about. And the same with a picture of Jimmy Page playing his Gibson guitar. There, however much you analyze this image, and we can do that analysis, there is more understanding to be gained from treating it in the same way that a human does. All of that wraps up in that we often speak of idle as the operating system for human information. What we mean by that is we encapsulate a huge amount of functionality within idle, and we expose it in a way that allows people to create systems, intelligent systems around it. There's a huge amount of complexity in how that works together, and I'm not going to delve into that today, but do keep following the series to find out more about how it deals with file formats and connectors, the different file types that it can handle, all around the scaling, the scalability and the security around idle. There's any number of pieces of stuff that I'm not going to have time to go into today. But what I will mention quickly is the type of functionality that idle is capable of. There are many hundreds of pieces of functionality that idle covers, and so any big list will leave you feeling like you don't have an understanding of what idle can do. So what we've done is we grouped them up into any one of four categories that begin to convey what idle can do. So firstly, you can search your data. You can give it a criteria of keywords. You can give it a Boolean expression. You can give it natural language, or you can give it a set of documents to retrieve your data back. You can search by example, but either way you retrieve documents. You can perform analysis on your data, give it a set of documents, and ask it to summarize the concepts that are within this, to create a category from some of them, or to find anomalous behavior within that data, or find a pattern, something like that. Once you bring people in, you can personalize your data. So the way that a human interacts with the system and looks at the data, writes data, contributes to things, and the edits that are made, you're able to build up an understanding of what that person likes to read, likes to work on, what their skills and expertise are. And with that, you can retrieve relevant information automatically for that person, so that everybody's view of a page is tailor-made for them. You can tie people together, so that when you're working on a project and you need some help, you can find an expert on the other side of the world that you didn't know existed. And the data enhancement is a huge one. So when it comes to text, it's adding fields that are not there, adding information to the data that isn't in the data itself as a field. So an example is determining whether a tweet is positive or negative, determining whether a news story, what is it about? Is it a sports document? And if so, is it about Formula One? Is it about football, tennis, cricket, whatever? And with audio and video, the sky's the limit, really. Enhancement of information from audio could be speaker recognition, language detection, and things like that, speech to text. And with a video, it could be something like face detection, finding logos on a screen, grabbing the text of a scrolling news. So there's a huge amount of pieces of functionality within the improve pillar alone. If you're interested in any of these, then I certainly recommend you have a look at idleondemand.com, which is our new web services offering of idle. And it's a great way of familiarizing yourself with what idle is capable of. It's exposing a lot of the top 10 pieces of functionality. There's an awful lot more will be coming very soon, in a way that allows you to start playing with it, to start writing your own applications, to start getting the power out of idle that can help your need. Right, so now let's get into some of the real techniques, the technology behind idle, the stuff you won't read in our in our marketing and literature. There are two main techniques that are used to underpin the way that IDLE thinks. The first of these was born in the 18th century, but to understand it, it's better if we go back to the 17th century and the foundations of probability. One of the big areas that has been a trigger for new mathematics is an ability to make, is desire to make money. And in those days, gambling was a big, a very popular pastime. And there was a particular dice game which people would play, and it was the first person to reach 20 points who would win the game. But sometimes the game was finished. One of the people had to leave, or they ran out of time, and they were only halfway through the game. So if a person was 12 points to 7 up, and they had to stop, then it's fairly clear the person who has 12 points should get a higher stake of the share of the money. And but how much more would they get? How much more likely are they to win than somebody else? Well, this required mathematics that hadn't been invented yet. So it was in fact Pascal and Fermat who created a whole new area of probability theory to try and solve that problem of how to deal with the dice. But it took another 100 years before somebody asked a very basic question. How do we know that the dice are fair? The whole of the math that they generated was predicated on the knowledge that it would come up, a dice would come up as a 1 in 6 at a time, it would come up as a 2, 1 in 6 at a time. But how do we know that that's the case? If you were in a casino and you were watching people playing dice, and it kept coming up as a 6, then you'd think there was something odd going on. You'd be betting that another 6 came up. Maybe this dice isn't quite fair. So how on earth do we test the dice is fair? Well, the answer came from a very unlikely source. It was an amateur mathematician who happened to be an Anglican rector in the south of England in the 18th century. And he created a new branch of mathematics to try to prove the existence of God. He didn't succeed in that process, but what he did do was the whole framework of mathematics on how to analyze data to determine how you update your model according to that data. Here's a few equations for you. If you go back to your high school mathematics, then everything you have in that will allow you to derive Bayes' theorem. I'm not going to go through the derivation here. One thing is clear, the bottom line there is Bayes' theorem. All that is a two-term equation, and in that is encapsulated the sheer power of Bayesian inference. And it seems that how can such a simple equation do that? Well, I'm going to talk you through a few examples, and hopefully we'll get a bit more insight into how something this simple can be so powerful. This is quite a famous example. I don't know whether you've come across it before, but in the early 1980s there was a game show, and so some contestants would try and win through to be the winning contestants, and whoever won would go to the finals board to try and win the star prize. And the winner would be presented with 3 doors. Behind 2 of those doors, we were told, was a goat. Behind the third was a car. It was assumed that the winner would want to try and take home the car. I don't know whether they actually got a goat if they won that one. But they were asked to pick one of the doors. So in this case, say for example, the contestant picked door number 1. What would then happen is that the host of the game show, who happened to be called Monty Hall, would open one of the other doors. Now the host knows where the goats and the car are, and so in all cases Monty could pick one of the doors, guaranteed to be able to pick one of the doors to show a goat. So he would always open a door that would show a goat. Once that was done, he would present the contestant with a dilemma, saying, okay, so I'm showing you goats behind door number 3. I'm now going to give you the option to change. So would you like to change to door number 2, or do you want to stick with door number 1? It's interesting if you have a quick think about that. Should you change? There's 3 options here. Have a think about which you'd pick. Should you definitely stick with door number 1? Should you definitely stick with change and go to door number 2? Or does it make no difference? What do you pick? Well, if you said that it makes no difference if you change or not, then you're in extremely good company. But unfortunately, you'd be very wrong. If you stick with door number 1, then you only have a 1 in 3 chance of winning the car. If you change to door number 2, if you decide to change your mind, you will be doubling your chances of winning. It goes up to 2/3. And this seems very counterintuitive. Surely it's just as likely to be behind door number 1 as door number 2. It makes no difference. And in that sense, you'd be right. But what we've been given here is some extra information by the host. Perhaps you think about it, if you look at the picture there, the probability that's behind one of door numbers 2 and 3 is 2/3. That's not going to change. The fact that the host opened door number 3 to reveal the goat, that hasn't changed a thing. There's still a 2/3 probability that's behind one of door 2 or 3. We now know it's not door number 3, so it's twice as likely to be behind number 2. When this show was on, somebody wrote an article in a magazine explaining this was the case, and the contestant would be twice as likely to win if he or she changed their mind. The magazine then got 1,000 letters from people around America, including 100 different math teachers and math professors, saying that analysis was wrong. Of course it makes no difference whether you change your mind or not. But in fact it does. And if we put the numbers into Bayes' theorem, which we've done on the top line here, the mathematics backs us up. So in this case, Bayes' theorem is telling us something that the intuition is not. Here's a second example, an even trickier one then. We have a normal pack of cards that we've shuffled. I take the top 2 cards off the pack. I look at them, and I say to you, one of them is an ace. At least one of them is an ace, in fact. What is the probability that the second is also an ace? That's a mathematical question that you could work out or not. How about instead if I said, one of these cards is the ace of diamonds, what's the probability that the second card is an ace? Now that's maybe quite hard mathematics to work out the probability there, but surely the probability is the same in both cases. Well, in fact, again, you'd be wrong. In fact, it's twice as likely in one case to be an ace if I've told you that one of them is the ace of diamonds. Now here the intuition really does fall down. If you've got the idea behind the goats and the doors, then this one, it's very tricky to give any understanding. But basically, again, if you put it into Bayes' theorem, the numbers come out straight away and give you the probabilities and shows their difference. But the key point here, and I'm getting at, is that the intuition is very wrong, often in many cases. Going into a system with a predefined model of how you think things will behave will often cause trouble, because data isn't like that. The real world has a lot of surprises. What Bayes' theorem is very good at is giving us a way of updating our knowledge according to the information we're given. The information that the goat is behind door number 3, that is information that we can use to update our model on where the car is. And Bayes' theorem tells us how to do that. The fact that I've told you it's the ace of diamonds rather than an undisclosed ace, again, that gives us extra information that we can feed into the model, Bayes' theorem in this case, and update it accordingly. Another example that will perhaps start to ring true here. If we ask the question, we toss a coin 50 times, what's the probability of getting ahead on the 51st? Well, probability says that the answer is 50%. Of course, mathematics tells us that. But how about then? What if we've tossed the coin 50 times and we've been watching it, and every time the coin has come up heads? What is the probability of getting ahead on the 51st toss? Well, again, the mathematics would say that that's 50%. The model has no way of updating itself according to the fact that we've just seen 50 heads. Now, if you were a human, were watching, then you'd be absolutely sure that the coin has 2 heads. As a human, we're built to work in a Bayesian way. Humans start with no information as to how the world works. All the observations that we see allow us to update our model and thus act more intelligently as a result. We would be absolutely sure, if we saw the coin being tossed, the heads just keep coming up, you would say with very, very high certainty that the coin is fixed, that the coin has 2 heads, or it's biased in some way. There's something dodgy going on. So humans work in a Bayesian way, so it's natural that we deal with human information in a Bayesian way. The second theory that we use in IDLE extensively is Claude Shannon's information theory. Claude Shannon is one of the real unsung heroes of the 20th century. He deserves to be a lot more famous because the theory that he generated, information theory, is used so extensively today, it's impossible to imagine life without it. The world of the web could not function without information theory. All compression and communication, CDs, DVDs, and everything like that is all based on theories that he came up with. How he did it, it was one of the greatest doctoral theses of the 20th century, in that he single-handedly created this new theory on how to put a price on information. What information is valuable, what information is not valuable. He also, as a matter of fact, managed to create a juggling machine, a rocket pad, frisbee, motorized pogo sticks, a mind-reading machine, and a mouse that could negotiate a maze. So he really was an amazing technical theorist, but we're going to concentrate on information theory this time. A quick example of how we can see information theory, what the core tenets behind it are, is to look at Morse code. And Samuel Morse designed Morse code 100 years before Shannon came up with the concept of entropy. But in it is the basic idea of what is going on. The main thing we notice here is that the very common letters, E and T, in this case the vowels, are encoded using fewer dots and dashes than the rare letters as X and Z and Q. Why is that? And that's a way of compression. So that's a primitive technique, and it shows us how to use entropy, that common information perhaps has less value, has less information than something that is rare, something that is unusual. Information theory is also used in image formats. For example, here we've taken a picture of a familiar scene, to many of you, the Toronto skyline, and we've removed 3/4 of the information by using a cosine transform. Still, it looks largely unaffected to us. It maybe looks slightly grainy, but when we've taken away 3/4 of the information, all the key aspects are still there. In fact, if we take away 99% of the information, then we're still left with a scene that is recognizable, even if you wouldn't want to print it out and put it on your mantelpiece. The key point here is, what information should we be taking away to leave what's important behind? And the information theory gives us that information. It puts a price on information. Another example will help to clear this. Here we have a piece of text, the kind of piece of text you'd find in any human information. The penguin, now it all became clear. What is the text about? As a human, we could form some theories. We could try to decide what this is talking about. But we need context. Batman realized the master criminal was at it again. So we see now penguin is actually, we're talking about the Batman's enemy. The publishing house that outbid us again. Oh, hang on, it's the same text, but I've got a little different context here. Now they're talking about Penguin, the book publishing company. Or the smell of rotting fish was unmistakable. This time, actually, we do mean penguin the bird, which is probably our first idea. So humans deal with information based on context. We allow that to update our knowledge on what something is about. So a keyword search for penguin, anything that is lacking the information we have to decide on this. Only a system that begins to understand context and the information as a whole can begin to understand things beyond that what we mean by the keyword. Another example here then. So he saw the black and white flash enter the cold sea and then a beak with a fish in its surface. This time it doesn't mention the word penguin at all. Yet as humans we could tell probably, not definitely, that this is talking about penguins. Humans deal with information in a very unusual way. They deal with what's called low-value information. A 10-minute conversation is full of low-value information. If you get to the end of that 10-minute conversation, you can boil it down to perhaps a 30-second snippet, which really gets at the heart of what the conversation was talking about. Computers are very good at dealing with high information. So we need something that's able to translate between them. So I've given you a very quick taste as to how we use the mathematics behind the scenes to really drive the understanding that IDLE is able to provide. I've only scratched the surface, so I hope the bits you understand, you'll get the questions coming in, and I'll try to answer as many as I can over the next few days. But with that, thank you very much, and thank you for listening.
Okay, thank you, Sean, for all of that great information. Before we close today's session, we ask that you please complete our survey. Simply click the link appearing on the bottom of this slide. All relevant information is forwarded on to Sean and other subject matter experts, and they all appreciate your comments. So audience, if you have not done so already, please submit your questions in the QA box and then click the Ask icon. We are very short on time today. I'll be gathering your questions and packaging them up for Sean, who along with his team will respond to you. We'll give you a few moments to get your questions in. I did see a few questions for a copy of the PowerPoint presentation, and unfortunately, we will not be distributing it today. If you missed any of today's session, it will be available in about an hour using the same registration link found in the invitation. I'd like to thank Sean again for a great presentation. That concludes our session today. Thank you all very much for your time, and have a great day.